Hello everyone, thank you for coming here today. We are Team 11. Today we will give you a brief overview for our team project. The presentation will be broken down into 7 main points. First, the introduction of the project. Second, vehicle model description. Third, performance analysis and controller design, simulation result analysis, and finally the conclusion.
This project had 3 main goals, all underneath the overall task of designing appropriate and effective controllers to simulate the lighter-than-air vehicle in flight. The 3 sub-goals were to hold a specified altitude, hold a specified heading, and then track a target moving in circular motion. In order to accomplish this task and subsequent goals, we used MATLAB and the proprietary software Simulink.
So the vehicle model, as described in the project description, it is a lighter-than-air robot or blimp, and it is controlled by 2 sets of propellers, with one set facing upward and the other set facing forward. And therefore, these 2 sets of propellers can introduce 3 sets of separate motions, with the first one being the linearized longitudinal dynamics, the second one being the linearized rotational dynamics, the third one being the linearized forward dynamics in the lateral mode.
This is our open loop system performance analysis. In this page, we show the percent overshoot, settling time in seconds, and steady-state error for each of our open-loop system model. The percent overshoot and settling time are calculated by MATLAB function step-info, and the steady-state error are calculated by hand. As shown in these slides, for longitudinal motion, the overshoot is 0% with settling time about 235 seconds and steady-state error of 52.9%. For the rotational motion, the overshoot is almost 100% with settling time about 168,000 seconds, and the steady-state error is about 0.03%. For the forward motion, the overshoot is 0% with settling time about 28.7 seconds, and the steady-state error of 0.23%. This is the root locus of the forward mode. We use MATLAB to draw it.
In order to design a controller for longitudinal motion, our team has built a model in MATLAB Simulink, as shown above, where the input is a step input from 0 to 1 since the airship will hover at 1 meter height from the ground. The linearized longitudinal dynamics for the vehicle are represented as a transfer function in the open loop system. In order to reach the desired system response, we choose to use the PID controller to optimize the system with a feedback loop. In the turning progress, we use MATLAB building tool called Control System Trainer by tracking the step commands in goals, where we assumed the second order characteristics with a time constant equal to 1 and maximum overshoot less than 5%. As a result, the improved PID values are 0.086 for the proportional gain, 0.0342 for the integral gain, and 0.2175 for the derivative gain.
For the rotational motion of the airship, we use the transfer function for rotational motion given in the project file to construct a plant with a PID controller with step input, a closed feedback loop outputted to a scope to observe the motion of the airship, wherein the gains were optimized by running the control system's tuner toolbox, and ultimately we obtain a proportional gain, an integral gain, and a derivative gain. The following parts of the project utilizes data from the results obtained in this slide.
This is the PID control for the forward mode. We follow the same steps as mentioned in the earlier slides, which mainly build the Simulink model in MATLAB and apply control system tuner to tune the system and then to achieve the desired goal. After tuning, our goal is met with the proportion value of 292, integral value of about 50, and the derivative value of about negative 132.68.
For the closed-loop system performance analysis, our team utilized a PID controller to attain better response for the vehicle. We also constructed Simulink models for different motion and used control system tuner to calculate the PID values with different assumptions. Our assumption includes a unit step input and a second-order approximation with time constant 1. Additionally, the system should have less than 5% overshoot and less than 10% steady-state error. Here is an overview for the system performances after the PID controller is designed. For the longitudinal motion, the system has a 6% overshoot and a settling time of 6.85 seconds. For the rotational motion, the system is able to achieve a 0% overshoot and a settling time of 4 seconds. Lastly, for the forward motion, the system has a 9% overshoot and a settling time of 6.56 seconds.
Now we'll move on to the simulation results. The first simulation we ran is to hold the altitude at 1 meter. As we can see from the plots, the output from the simulation tells us that our system will rise to our target in under 5 seconds and will slowly decrease and hold at that altitude for the rest of the simulation. Since we don't have any heading inputs, the output will also be 0. And we set our speed to 0.3 meters per second in the positive x direction. And from the results, we can see it reaches that target and settles within 5 seconds and will keep on holding that velocity. And we can see from the trajectory, it is performing as what we were expecting. It will rise to our target by overshooting it about 5 centimeters, and then slowly decrease and hold that altitude while moving in the x direction at about 0.3 meters per second.
I'm Chad Blackwell, and I'm going to be covering the rest of the simulation results. So for heading control, we were able to reach our final value of 25 degrees within about 10 to 15 seconds, and it was actually able to get within 5 degrees almost immediately. This is the 3D trajectory. I was fighting with MATLAB for a while to try and graph the grid lines so that you could get a better 3D perspective on what was happening here. And I wasn't able to figure that out, but trust me, it's going 25 degrees. Up next, we have tracking a moving target, and this one proved to be interesting. Now, for our model, this is able to account for both rotation and speed control at the same time. Realistically, that would not be possible. This is the 3D trajectory for the blimp. As you can see, it sticks pretty closely to the trajectory of the target, and that's due again to the fact that we're able to control both speed and heading at the same time.
Overall, introducing a pig controller yielded much better system responses. For all types of motion, we were able to decrease the settling time by drastic margins and the steady-state error, or even eliminating the steady-state error entirely. However, for the longitudinal forward mode motion, we had to introduce some percent overshoot. The altitude hold simulation yielded virtually no error in the heading. Lateral forward motion yielded roughly a 5.2 second settling time with no steady-state error, and the height response was the slowest with a 1% steady-state error and a roughly 20-second settling time. For the heading hold simulation, lateral and longitudinal responses were nearly identical to that of the altitude. The rotational motion, however, was the slowest to the response. And the tracking simulation, the blimp tracked the target in an 8-meter radius, where accumulating an error of 2.6281% over the course of the simulation. It is important to note that the simulation did not account for rotational/forward lateral switching.
Overall, after completing the project, our group has a deeper understanding of designing a control system for a real-world application using MATLAB and Simulink. We successfully demonstrated the use of overshooting percentage, settling time, steady-state errors, root locus, and PID tuners through our MATLAB code using the step info, step, absolute, and rlocus functions. For part D of our project, we simulated an altitude hold and heading hold as well as the tracking of a moving target. Possible errors when performing our calculations are the assumption that there was no external forces, user coding, and MATLAB rounding and step size.